welcome to this presentation about WebAssembly, also known as Wasm. It's an exciting new technology. We will be exploring how it works and how it fits in the Docker ecosystem. I'm joined today with my co-worker, Asen Alexandrov. He's one of the members of Wasm Labs, which is a team at VMware's office of the CTO of developers building tools for other developers working on WebAssembly. You can check it out at wasmlabs.dev. Everything that we do is open source and we build it in the open. So what is WebAssembly? WebAssembly at its core is a binary format. It's a way of defining executables, and it's also an open standard. So you can compile programs to WebAssembly and run them on a variety of environments. WebAssembly started in the browser side, and nowadays all of the major browser platforms from Chrome to Safari support WebAssembly. So what does that mean? What that means is you can take a program written in a language like C or C++, or even more modern or more recent languages like Rust and Go, and you can compile that source code into a WebAssembly binary. Then you can take that WebAssembly binary and run it inside the browser. Typically, the WebAssembly runtime that runs the binary is co-located with the JavaScript engine. So if you're using Chrome, the WebAssembly runtime will be part of the V8 JavaScript engine. By default, the WebAssembly runtime is completely sandboxed and cannot access the outside world. The only way to communicate with the outside world is through bindings. In this case, bindings to the JavaScript engine, which in turn allows WebAssembly to access indirectly HTML and CSS. From that perspective, you can think, even if the comparison is not entirely accurate, you can think of WebAssembly as Java bytecodes and the WebAssembly runtime as the JVM. So what can you do with WebAssembly? With WebAssembly in the browser, you can run video games, you can run like design applications like Adobe Photoshop or Figma, which is now part of Adobe, or Google Earth used to be like a completely desktop application that now you can access just by going through a URL. So it's having like a high performance environment for running programs that traditionally used to be desktop-like in the browser. So that's very interesting, but you're probably wondering why I'm talking about WebAssembly in a Docker community day, in which Docker for the most part is technology that is for servers or is for developing on the command line, is not for developing browser applications. All goes back to this tweet by Solomon Hykes, which was one of the co-creators of Docker, that if WebAssembly plus an associated standard called the WebAssembly System Interface had existed in 2008, he wouldn't have used Docker. And that's how important this technology is and why that technology is the future of computing. So those are big words. By the way, I agree with Solomon. Let's explore it a bit. What does that mean, right? So what that means is the first part of the diagram that I showed before is exactly the same one. You still get the source code for the program that you want to run in WebAssembly. You compile to the WebAssembly binary, and it still runs in a Wasm runtime. But that Wasm runtime, since you cannot rely on having a JavaScript engine, actually interacts with the outside world or interacts with the operating system through a different set of interfaces. One of them is the WebAssembly System Interface that I was mentioning earlier, but there are also other interfaces for dealing with networking, dealing with database access, with neural networks, and so forth. So why would you want to run an application in WebAssembly on the server side versus wanting to run that same application natively? So WebAssembly provides a bunch of features that make it a very interesting choice for running it on the server side, not just in the browser. The first one is a completely open standard that has been widely adopted. So companies as varied as Docker and VMware, Intel, ARM, Google, Microsoft are backing this standard. It really is industry-wide. It's tremendously portable. It runs on all kinds of CPUs from x86 to RISC-V. Most operating systems, mainstream, POSIX, non-POSIX, real-time. It's also is very fast, and for many scenarios is as fast as native applications or close enough. It's also very efficient. It requires like a minimal, it has minimal memory requirements and CPU requirements. It can run in devices for IoT or devices that have microcontrollers. Because of the browser heritage, it has a lot of security-related capabilities. Is sandboxed by default. You cannot do anything unless you give it specific access. Just like when you access the camera in the browser, you need to give permission to that particular web page to access the camera. You have to give specific permissions, specific capabilities to the applications running on the server side to access the file system or access the network. And finally, is polyglot supports for a lot of different languages. The actual support varies, but it's getting there, right? It supports most modern toolchains. You can think of WebAssembly as both the evolution of traditional server environments or a new take that we're going to talk a little bit later. So the first take, you can think of WebAssembly as one step going from physical hardware, which is how we used to do things back in the 90s, to having virtual machines or cloud, which is basically virtual machines running on somebody else's data center, allows you to extract that physical hardware and have the unit of deployment being a virtual machine. So you take like an operating system, you take the applications, and you put that into a VM or a cloud image and run it. Then when Docker came along and popularized containers, you could run containers. You didn't have to worry about the operating system. You could just worry about the libraries and your application, and you could ship your application and all of the dependencies in a container that make it a lot more portable and make it much easier to automate or deploy. So each one of these have different levels of isolation, has different level of footprints. Like virtual machines, you typically are in the range of gigabytes of in terms of size. Containers tend to be hundreds of megabytes, low gigabytes. With WebAssembly, you can get into tens of megabytes or directly on megabytes. So in terms of size, it's kind of like the next logical step. And also in terms of isolation and kind of like the level of abstraction that you're doing is also like a step further. Has much more stronger security boundaries than containers, which use the Linux kernel processes. And in terms of abstraction, you only care about the program, you only care about the libraries, you don't care about the rest of the operating system, because there is no such concept of the operating system. So this is one way, and this is what you may have heard, that WebAssembly is going to replace containers, or is what comes after containers. There is a different take, which is to take a look at WebAssembly as an alternative to containers. So when you're using Docker, by default, you have this tooling that allows you to build containers, to run containers, that makes it easy for you to build and share these containers with other developers or other users. But you're sharing a specific type of containers, which is a Linux container, right? So when you're executing with Docker Engine and Containerd, it will have a shim that will call the right kind of backend to run the right process. So in traditional Linux environment, you will just start a process that has a series of restrictions, run C groups and what you can do, and that's, you're starting like a container process. You could keep all the tooling, you could keep all the user experience of Docker and replace those Linux containers with a WebAssembly module or a WebAssembly container. In that case, instead of using runc to start a container process, you will be using a WebAssembly runtime. In this case, for Docker Desktop, you can use WasmEdge to start a Wasm module. From the perspective of the user, very little changes, and from the perspective of the backend, now you have access to this new backend technology that allows you to leverage all the characteristics that I mentioned earlier. And we'll see that in the demo. Talk a little bit about WasmEdge. WasmEdge is one of many different WebAssembly runtimes that are in the market right now. We chose WasmEdge because it's open source and is part of the CNCF. It's quite popular. It supports a lot of different CPU architectures, from x86 to ARM to RISC-V, as well as a lot of different operating systems, all the mainstream ones like Linux, Windows, and macOS, but also a lot of more non-Linux based like real-time operating systems and others. It has been optimized for cloud native and applications running in the edge. There's a lot of other things that other more minimalistic runtimes may be more suited for. We believe that this is like a good balance. And then finally, it's extensible. They have been adding very quickly support for different technologies. Some of them are standardized already by the Bytecode Alliance, which is one of the foundations that are working on WebAssembly. And some of those are being standardized. Some of them WasmEdge is building on their own with an eye to when they get standardized, they will be contributing back or adapting to it. But if you want to use today, neural networks, you want to use AI inference, you can do so very efficiently with WasmEdge. There's a lot of networking capabilities. We'll be using some of those during the demo, and as well as integrated with the rest of the container ecosystem, including Kubernetes and Docker. Docker partner with WasmEdge for this initial version of Docker Desktop with support for WebAssembly, and you can go and check it out on GitHub. We are going to be using PHP for the demo of how to put all these different pieces together. And in contrast from when you compile like a file from C++ into a WebAssembly binary, with PHP, you do something slightly different. You don't compile the PHP application code directly to WebAssembly. There is not such a compiler or transpiler. What you do instead is you compile, or what we have done to be more exact, what we have done is compile the PHP interpreter, which is written in C, into a WebAssembly binary, and then that WebAssembly binary can read or can bundle that PHP file, then being executed on a WebAssembly runtime. Asen will go over this in the demo. As part of the work that we did in Wasm Labs, we ported the PHP runtime to WebAssembly. There were already like ports of WebAssembly to the browser using a toolchain called Scriptem. This toolchain leverages JavaScript functionality that you can find in the browser to emulate or provide networking and provide a lot of the things like a POSIX environment is expected from a POSIX environment. The WebAssembly system interface port that we are contributing back, it is focused on server environments. For that, we reuse or use tooling like WASI libc to emulate or stub out functionality that has to do with POSIX, like signals and getting process IDs and so forth, as well as remove functionality that it's either not needed. There is now the concept, for example, of processes in WebAssembly being able to execute other processes, or that were not supported, right? Some of them are there, and for the most part, file system access is there, but things like changing permissions on that will basically not work or be ignored. And with that, even with all these restrictions, you can run like very complex, very sophisticated applications like WordPress, and we'll be seeing that during the demo. So without any more delay, I will leave you now with Asen, which will put all these different things that we saw in this first part of the presentation in action. Thank you.
Thank you, Daniel, for the great introduction. Now, let's get our hands dirty with a few hands-on examples. We'll see what it takes to build the WebAssembly module, to put it into an OCI image, and run it on Docker desktop, along the line comparing it with the same running as a native binary. For the sake of this demonstration, we'll be using a PHP Wasm binary, which we built for another project. Then we'll compare what a running container behaves like in terms of WebAssembly container and a normal container. And in the end, we'll stress on the portability of WebAssembly and why WebAssembly plus Docker is much more than traditional containers. Building and running a WebAssembly container is not that hard. We start by using the normal PHP code source base, which is written in C. We use the WASI SDK package, which combines a compiler with WASI-libc, a runtime library compliant to glibc, and then we can get a php.wasm binary compiled to WebAssembly. Wrapping it up in an OCI image is very simple. The Docker files always start from scratch, and you just copy your Wasm image. And there you go. You have a container image, which you can use with Docker Desktop plus Wasm to run it just as you would any other normal container. Let's see what lies behind the step of building. Now, this is our simple build script. The important thing is that you need to set your compiler, your linker, and everything else based on what you get from WASI SDK. And then you will run your normal configure or CMake or any other build system script almost as close as to what you are used to. So let's just do that. This is a normal autoconf script combined with make. Of course, we're not going to wait for it, so let's skip to the end. Now, we've got a few binaries here, but for the sake of this demonstration, we'll use only the ahead of time compiled binary. Without going into much detail, it will give us the best performance. What does it take to build this into a Docker image? I've got two Docker files here. One will just build a container with the simple PHP CLI command, and another will build a container with some built-in examples which get served on a certain port. The commands to run these Docker files are also pretty simple. Here is the script with them. And now let's run the script and get those images. Pretty fast, but that's all when the only thing you have to do is just copy. Let's take a look at those images. Here they are, PHP Wasm, and a very small size. For the sake of our next demonstration, we'll be using the same index.php file and running it with a native PHP binary and a WebAssembly-based binary and comparing the results. So let's take a look at the index.php file first. We'll just print the PHP version, the platform on which the interpreter is running. Then we'll get a list of the environment variables available to the script. Then we'll just print the current date and time to say hello and print the contents of the root folder, which is also available for access to the script. Now, let's compare running this natively versus running this with WebAssembly. Here is our plan. We start with the index.php file that we saw. We'll first interpret the index.php file natively, running on my machine. Then we'll interpret it using the PHP WebAssembly module running inside of a Wasm runtime, in our case, WasmEdge. Let's run the native app and see what happens. And as a result, we get the version, we get our platform, Linux something, we get a huge list of environment variables available to the script. This could be some kind of a security implication, because God knows what's in that script. Then we also get a list of all the contents of the root folder on my machine. Let's compare to the same thing, but in WasmEdge. Take a look at this. We have the same version. The platform, however, is WASI. That's short of WebAssembly System Interface. We don't have access to any environment variables. The time is correct. And we have absolutely no access to get the contents of the root folder. Because with WebAssembly, you can only access the files and folders which are pre-opened whenever you run the WebAssembly binary. So in our case, there will be a folder called docroot, and it will contain whatever is in this folder on the host machine. And that's the only thing that the file system inside of the WebAssembly program is capable of accessing. So that's why we get capabilities insufficient and absolutely no access here. The same goes with environment variables. You can set additional environment variables whenever you run the WebAssembly module, and you will have access to them. But in our case, there is nothing. What actually happened is that by just compiling PHP to WebAssembly and running the same index.php script there, we get automatic security. Now let's move on and see how that behaves when you use Docker. On the top, we'll see what a traditional container looks like running the native binary in a PHP 7 432 image base. And at the bottom, we'll see what our PHP Wasm image base produces in terms of a container. Running the native image in a Docker container looks like this. We see something similar, same version of PHP. We see again the Linux kernel. Of course, we see fewer environment variables, in this case 14, because this is all running in a container context and is more secure. And the contents of the root folder is also limited, but still, we do have access to a lot of stuff. Let's take a look at what running this with WebAssembly in Docker looks like. Of course, we'll need to provide a specific runtime and platform. This may change with time, but that's the way you do it now. Then, for the sake of mapping the doc root folder, we use the well-known syntax from Docker. Here we still have improved security. First, there are only two environment variables inside for the sake of infrastructure, path and hostname. Then the contents of the running container is just the doc root folder and an infrastructure etc and the PHP Wasm binary, and that's all. And now let's take a quick look at the differences we can see with a plain eye between traditional containers and containers based on WebAssembly. For the sake of this demonstration, what I'm going to do is I'm going to run the PHP server natively and with WebAssembly, exposing some port here and the doc root, and again exposing another port here and doc root, where again we will serve index.php. Now let's do that. We will be running daemon containers, which will stay in the background, and this will allow us to see statistics, behaviors, memory, etc. Here we see that we are serving the index.php file all right, and we are listening on 8081. And now let's run the WebAssembly version of this thing. And we're listening on 8082, again serving index.php. Now, let's see what those running containers will show us in terms of stats, numbers, etc. Running the Docker stats doesn't show much yet, because for WebAssembly, not everything is still implemented, but we can use the interface to monitor control groups if you want to get a little bit more information about what's going on. Now, something of interest here is that traditional Docker containers get their own control group, so you'll see them here, but WebAssembly-based Docker containers are all within the pod runtime Docker control group. So if you're monitoring what your container consumes in terms of memory and resources, you could be watching what goes on here when you spin up more and more WebAssembly-based containers. And finally, let's take a look at the different images. Normal PHP images take a lot of space, and that's expected because in those images, you get an image of the operating system with lots of runtimes, libraries, etc. With WebAssembly, you only need the WebAssembly binary. The runtime is embedded into Docker Desktop, and you just use it as is. And we have summarized this difference here. Traditional images get you lots of stuff which you may not necessarily need. WebAssembly-based images get you just what you need in order to run that application. For the last part of our demonstration, we'll talk about WebAssembly portability. Why is that important? Docker gives us portability in many ways. You can build your machine here and ship it somewhere else. But that's with a catch. It will work only if the recipient has the same architecture. Now, of course, there are cases where the recipient may run a virtual machine with emulation and stuff and still be able to run your Docker image. But let's face it, we often have to build different versions of the same image to be able to support different architectures. With WebAssembly, that's not the case. You build once and you run it everywhere, and that's a promise. Now, let me give you a short demonstration of how that works using the PHP interpreter, which we already have, and running WordPress in it, and running it on different platforms. We'll run it on WasmEdge locally on my machine. We'll run it on Docker using the WasmEdge runtime, which we already demonstrated. We'll run it inside of Apache using mod Wasm. which embeds a WebAssembly runtime and can interpret the WebAssembly modules freely. And then we'll show how WordPress works in a browser, again leveraging our PHP interpreter compiled to WebAssembly. Let's go. So first, we are running WasmEdge locally. And you can see, here goes WordPress. Now, we're going to use the same PHP Wasm binary and run it inside a Docker container. And then we'll move on to do this with Apache, as I said, and a browser. So here we are running WordPress in Docker. And now let's run this in Apache using mod Wasm. Of course, I don't have Apache installed locally, so I'm going to use a traditional Docker container to run it, which takes a little bit more time just to load the container and Apache inside. But in the end, here we are running WordPress, interpreted by the PHP WebAssembly module, loaded by WebAssembly runtime inside the mod Wasm extension to Apache HTTPD. As a final step, let's run WordPress in a browser. And here it is, again, interpreted by a PHP WebAssembly module, but this time running inside of your browser. So, as a recap, we showed what it takes to build a WebAssembly image and put it into a Docker container, how easy it is to run it, what are the little differences that you can see when you run a traditional container versus a WebAssembly-based container in Docker Desktop, and then what's the big deal about WebAssembly and why it seems to be the true promise of portability. If you want to run any of these examples, Daniel will provide you with a link which you can check out after the demonstration.
That was a great demo by Asen that hopefully let you visualize some of the concepts that we described early on. Thank you for watching. Please follow us on Twitter or go check out and try by yourself at the URL at the wasmlabs.dev/docker. And looking forward to getting your feedback and maybe getting involved with the project. Thank you.